You step outside tonight. The sky is clear. And you notice something strange. A star you've never paid attention to is suddenly brighter than the moon. Bright enough to cast your shadow on the ground. Bright enough to make you squint. For about 6 seconds, it is the most beautiful thing you have ever seen. And then your phone dies. And then your neighbor's car stops working. And then the sky turns red. That is not a horror movie opening. That is precisely what scientists calculate would happen if a star within 25 light-years of Earth went supernova tonight. And here's what no one tells you: there is at least one candidate already showing the signs. To understand what this would actually feel like, you first need to understand what a supernova is. A supernova is the death explosion of a massive star. Not just any star. A giant, something between 8 and 100 times larger than our own sun. For millions of years, that star has been fusing lighter elements into heavier ones, burning hydrogen, then helium, then carbon, fighting against its own gravity. A constant battle between fire and collapse. But when a star starts fusing iron, the process stops producing energy. And in less than 1 second, less time than it takes to blink, everything changes. The entire core, a mass equal to our sun, collapses to the size of a city. In 1 second. And what follows is the single most violent event in the known universe. A supernova releases more energy in a single second than our sun will produce across its entire 10 billion year lifetime. Now imagine that explosion happening 25 light-years from where you're sitting right now. To put that in perspective, our nearest stellar neighbor, Proxima Centauri, is 4.2 light-years away. 25 light-years is not the edge of the galaxy. It is our cosmic backyard. And inside that backyard, there are candidates. Here is the most unsettling part of this entire scenario. If a star 25 light-years away went supernova right now, you would have no warning. None at all. Because the thing that kills you travels at the speed of light. By the time any telescope detected the explosion, the first wave of gamma radiation would already be arriving. No alert. No evacuation order. No time to get underground. The first thing you would notice, if you happen to be looking up, would be a new star. Brighter than the full moon. Bright enough to cast your shadow on the sidewalk at midnight. You might even think it was beautiful. For approximately 6 to 12 seconds, it would be. And then everything that runs on electricity begins to fail. Hour 1. The gamma ray burst has arrived. You cannot see it. You cannot feel it, yet. But in the upper atmosphere, high-energy photons are slamming into nitrogen molecules at near light speed. This reaction destroys ozone, instantly. Across the entire hemisphere facing the explosion. Within the first hour, satellite systems begin behaving erratically. GPS signals drift across entire cities. Long-haul airline communications drop out mid-flight. Power grids across the affected hemisphere begin experiencing cascading fluctuations as the Earth's magnetic field responds to the electromagnetic pulse. Government scientists know something catastrophic has happened. But the data streams are failing, and no one has a model for this. Not in peacetime. Meanwhile, outside, the sky has turned a color that has no name in any human language. The aurora borealis is now visible from Miami, from Cairo, from Bangkok. Families are coming out of their homes to watch, filming it, posting it, calling it a miracle. And in that moment, humanity is still completely unaware that this beauty is a symptom. 6 hours after initial impact, the first human casualties appear. Not from fire. Not from shockwave. From sunburn. With the ozone layer critically degraded, ultraviolet radiation from our own sun is now reaching Earth's surface at levels 10 to 100 times higher than normal. Anyone who was outside during daylight hours is experiencing severe burns, not just on their skin, on their corneas. Mass blindness events begin across Australia, Southeast Asia, and Southern Africa, the regions with peak sun exposure at the time of impact. Governments issue simultaneous global shelter orders. Stay inside. Do not look at the sky. Do not go outdoors between sunrise and sunset. But here is what scientists understand, and what no government announcement will say aloud. The ozone layer does not recover in days. The models show a minimum of 3 to 6 months of critical degradation. Some models show partial permanent loss. The scientists run the numbers twice. The results do not improve. And then, 3 months after the initial flash, something else arrives. Not radiation this time. Physical matter. The ejected mass of the dead star itself. Charged particles. Cosmic dust. Heavy elements forged inside the dying star, now racing through interstellar space toward our solar system. As this stellar debris begins interacting with our sun, solar activity intensifies dramatically. Solar flares erupt at frequencies never recorded in human history. The electromagnetic pulses from these superflares are powerful enough to permanently destroy unshielded electronics, across entire continents, within 72 hours. 1/3 of Earth's power grid infrastructure is either damaged or completely destroyed. Cities go dark. Hospitals switch to generators. Communication satellites go offline permanently. But the cosmic dust, the physical remnant of the dead star, begins something far slower and far more permanent. Global temperatures begin to drop. Not like a disaster movie. Gradually, 0.5 degree in the first month. 1 degree by month 3. 2 degrees before the first year is over. 2 degrees sounds manageable. 2 degrees is not manageable. 2 degrees means the agricultural zones that feed 3 billion people begin to fail. Within 18 months, the cascading failures begin. First the food systems. Then the energy infrastructure. Then the political frameworks that depend on both. Civilizations are extraordinarily resilient, history has shown us that again and again. But civilizations require one thing above all others: predictability. Predictability of seasons, of sunlight, of food. A 31% reduction in global food production does not mean 31% of people go hungry. It means the most vulnerable 31% face starvation. Roughly 2.5 billion people. And every empty hospital. Every military checkpoint. Every government that falls. Every family that doesn't make it, all of it traces back to a single moment. A star, 25 light-years away. That no one saw coming. Now here is the part that scientists don't like to discuss at press conferences. In 2019, the star Betelgeuse, the red giant in Orion that you can see with your naked eye right now, dramatically dimmed. Astronomers called it the Great Dimming. They said it was a dust cloud ejected from the star's surface. Betelgeuse will go supernova within the next 100,000 years. At 700 light-years, we would be affected, but probably survive. Betelgeuse is not our concern tonight. There is a binary star system 150 light-years from Earth called Pegasi. It contains a white dwarf, slowly pulling mass from its companion star. Building. Accumulating. Moving toward a critical density threshold. When, not if, when that white dwarf crosses the Chandrasekhar limit, it will trigger a Type Ia supernova. The most consistent, most powerful category of stellar explosion in the universe. 150 light-years is inside the danger zone. By every model we have. And astronomers have no confirmed method of predicting exactly when that threshold will be crossed. It could be 1 million years from now. Or it could be tomorrow. The universe does not negotiate. It gives no warnings. But knowledge does something that survival instinct cannot. It prepares us for what's coming. If you want to know what happens in the first 60 seconds after Earth's rotation suddenly stops, and why the oceans move faster than any tsunami ever recorded, subscribe to ImagineIf, because the next impossible scenario might not be as impossible as you think.